It's something which could become, in the next 3, 4, 5 years, a very, very hot topic. And just to give you some quotes, starting with the first one, a quote from official from Microsoft, and he says that a combination of advanced software and internet-based services can help people track, understand, and manage their personal energy use. And this guy from Microsoft was actually commenting on a smart grid application that Microsoft is currently building. So Microsoft is entering into this business. Another quote from another company you know about, which is Google. And he says, "We believe consumers have a right to detailed information about their home electricity use, and homes must be equipped with an advanced energy meter called smart meter." And this is something which is already being implemented in some countries. Actually, we are going to simulate something which goes a little bit further. But what the guy of Google said, it's because actually Google has invested recently 100 million euro in a joint venture which will actually invest in this kind of technologies. And I think the last quote is probably even the most striking. The vice president of marketing at Cisco says that our expectation is that these smart grid networks will be from 100 to 1,000 times larger than the internet. If you think about it, some homes today have access to internet, but some don't. But everybody has electricity. So are we going in the future towards a convergence between the electricity grid and the communication grid? It's very possible. And using this will enable actually people to better manage their consumption of energy and go towards a solution to the two big challenges I was talking to you about. So this is for the general introduction. So what is now our objectives and what do we want to reach? So as Vincent said, we heard about hacking at random, and we knew that they were looking for papers including on this subject. And since we were already talking about this since a long time and that we knew hacking at random, we thought we're going to work on that. And so our objective was to build a simulator which is able to reproduce the behavior of decentralized power generation. Well, now, decentralized for us, it's the decentralization of power production. Today, one big nuclear plant can actually feed a city like Rotterdam. This is not decentralized. We have one big plant feeding 1 million customers. What we want to simulate is the power production which is actually close to the power consumption. We implement the extended smart grid concept, just like I told before, where actually all loads and all sources will participate to the system balance. The price will be the signal for the sources and the loads to adapt their behavior. And there is still one centralized element, which is the price settling mechanism through an auction. Then our objective, of course, is when we have this simulator, is to use it and to analyze the feasibility, the economics of all these ideas. The simulation setup. This is the global setup. What we are actually simulating is a virtual isolated village. Actually, today it doesn't really exist, but why not in the future? We imagine that we have a village, a small village of 100 households, which are fed by photovoltaic panels, which are also fed by some small wind turbines, and we have implemented also some batteries in the systems in order to balance more easily. We will simulate for this presentation one day, and every minute there will be a price auction. So, of course, in the future we want to have a more advanced system enabling to simulate a longer period, enable to simulate stuff which are not synchronous, because now we do it for 1 minute, but it's of course only the beginning of this implementation. Each household has actually a pretty stochastic consumption pattern. If you imagine yourself going home, you are consuming when you get back from work, you're consuming when you're switching on your washing machine, your TV. So every household is actually a very quite stochastic behavior. And the total of these behaviors, because of the equations we put in the back, well, it's actually a very standard load pattern for residential customers. You see in the very beginning of the simulation, the beginning of the day, that there is a high consumption. I will explain you why we have this effect. But except from that, it's a very standard load pattern for residential customers. It's very low in the morning, and then it starts increasing in the morning because you wake up, you switch on the light, and so on. And in the evening, you come back from work, you need again the light, you need a TV, and so on and so on. Our simulation setup, so we have some elements. We have one grid, which is the connection between all the components. We have 5,400 loads because we have 300 households, and in each household we have simulated each of the types of consumers. We have three types of load, and I will come back on that. We have the warm accumulator load, and we have assumed that each household has a small hot water boiler with a water accumulator. So you have a boiler with a small tank, and this enables you to switch your consumption for moments when there is electricity at cheap price. You have also cold accumulators, typically refrigerators, freezers, and so on. And then you have all the other types of loads, the lights, the dryer, the oven, and so on and so on. And actually each of these loads is implemented with its own logic. Then we have 153 sources. We have simulated one big diesel engine. Why? Because we still need a buffer. Okay? We still need to have this because in case you have no more resource, otherwise, there would be a problem. Then we have two small wind turbines, 150 photovoltaic panels, and 150 small batteries. I will go into some details for the loads. As I said, we have three types of loads. The warm accumulator loads. Typically, here we assume it's a warm water boiler with a small tank. The consumption behavior of this boiler is that it will try to consume electricity and so to heat up the water when the water temperature is low. But when do people use that water? Well, when the times you need. I mean, you need more water at 8 p.m. than at 4 a.m. So there is a kind of probabilistic function, and every minute we will check, is this guy needing some warm water? Yes or no, and then we check this. So each type of load has also some flexibility, because if the loads have no flexibility, our system has it has no point. So the warm water accumulator, it's kind of easy system to implement the flexibility. We say when the internal temperature of the water tank is very low, it will bid electricity at a very high price, which means I'm ready to put a lot of money to have my water tank heated up. But if I'm already full, I will bid at a very low price. And so the probability that it will consume at that time will be then much lower. Cold accumulators, it's actually almost the same principle, except that the timing are much smaller. Your fridge, you can stop your fridge for 15 minutes. The internal temperature will still be acceptable, but you cannot do that for 3 hours in a row. Then all the other types of loads, it's actually more difficult for these loads to implement flexibility. Because when you get home in the evening, you want to have your light, and you don't care if the electricity is expensive or cheap. You just switch on your light. However, since we still want to see to what extent this variability of the load can benefit the system, we have implemented a logic. The logic is that the first bid of these type of loads is at 20. We say 20 euro, but actually the price level, it's not that